metagenomics. You know, we can take DNA out of the ocean and you can find all the genes, but what does it tell you? Well, if I ask that rhetorical question, the answer is, of course, nothing. It tells you very little, because it tells you that there's nitrogen fixation, there's photosynthesis, there is digestion of proteins. Well, we know that. We see that. We see organisms collect light and grow, so there must be photosynthesis. Knowing the genes by itself doesn't tell you much. But if I know which organism has which genes, then I can say, you do photosynthesis, you do nitrogen fixation, and you eat those guys. So by being able to partition the ocean into individual components and then correlate those components with the metagenomics, you learn a lot. And you have to do that. You know, you need to know that there are whales and that the whales eat krill and that the krill eats algae. That tells you about the ecology of the ocean and how it might change with global warming, with fishing, with copper pollution. Those are the things that we need to answer. Again, this was done 2 years ago. At that time, 2014 was the warmest year on record. We are now in 2017, and we know that 2016 was even warmer than this, so it just shows how quickly this is changing. These were the warmest years recorded. They all happened between 2000 and 2014 and 2016. I think 2015 was a little lower, but 2016 is high again. I don't care. I'm in my 60s. But you guys should worry about it because you still have a lot longer to live. And by the time you are in your 60s, the temperature is probably there. So this is an important question. Important question, it's going to warm, and what effect will this have on life in the ocean? Because we think that life on land is important, but the ocean is 2 times bigger, 3 times bigger than the land mass. And what's happening in the ocean is really going to determine I think half of the molecules, or at least 1 in 4 molecules of oxygen that you breathe comes from the ocean. What happens if all that stuff goes away? The CO2 that we exhale is being processed in the ocean. It's partly by the trees here, but much more is going on in the ocean. We need to know what these global processes, how they are affected. So Citometría allows us to study directly how the physical environment reacts, like temperature, acidity, current, oxygen, irradiance, how those affect microbial life, because we can now look at the ocean at different places and see how microbial, the different microbes do change. So this is why I've migrated from immunology through molecular biology to flow cytometry of plankton. Officially I'm retired, but I'm still working with oceanographers trying to improve the equipment so we can better understand what phytoplankton looks like. But what we learn here can be applied back to immunology and molecular biology, so it's really all the same. And this is why I think you guys, being at the beginning of your career, being young oceanographers, have a great opportunity to study microbiology and environmental ecology and physics and technology to then get to what I think is one of the most wonderful scientific endeavors possible. And you are particularly lucky because you live in Chile, right? And Chile is actually not much of a country, right? That's not a country. But it's really an ocean, right? You go all the way from almost to the equator, all the way to the South Pole. And you have all that beautiful ocean there to study. You have the minimum oxygen zone here. You have the copper polluted waters, the rich salmon grounds in the south, the penguin waters in the south. There's so much to study here. And this is why I'm coming back. It's just whatever you do, it's new, it's interesting, and it's important. So And I think that's my last slide. Yeah, that's my last slide of this series. So, are there any questions about what I told you? Comments? You look like you have some.
Yeah. You said that you can apply this citometry, for example, in microbial ecology or something like that. In microbial ecology?
Yeah.
Or, I think that if you going to use citometry, you need like liquid.
Yeah, that's a good
matrix.
point. That's a good point. Yeah.
Yeah. So, how the citometry can study things like soil or other kind of matrix?
Very good point. Very good point. Yeah. So I did not talk about the limitations.
Very common.
It was really a sales talk. Yeah. But yeah, we look at one particle at a time, so we must have the particles in suspension, right?
Yeah.
If they're all sticking together, we cannot do anything. But there are ways of teasing things apart. In medical, in cytology, you can work with enzymes that bring the cells in suspension. There are people that work with protoplasts of plants, make the individual cells. In the case of soil, you could just suspend the soil in water, and then you hope that the microbes will be floating around. And that's really a severe limitation. The really interesting, or some of the interesting microbial communities are biofilms.
Yeah.
And now you have to ask yourself, is it still valid to disturb them? Because in the microfilm or in the soil you may have regions without oxygen, because there's a lot of iron, there's very steep oxygen gradients over maybe millimeters. So yeah, that is a limitation, but you know, maybe you can do something like this, where this is 100 meters, but maybe I can do this with 100 micrometers, right?
Yeah.
I go with a little pipette and somehow construct a way to take things out. But the major problem is going to be that the microbes do not have natural, they do not have natural pigments. And and that's the great thing about photosynthesis. So we know a lot about photosynthesis, but the same works in the ocean. The heterotrophs are basically invisible. And that's why I'm working on equipment now that uses light scatter rather than fluorescence to look at small particles. And the commercial instruments for hematology, for blood cell analysis, do not do light scatter very well. So especially for microbe research, I'm now trying to build systems that can see microbes and measure very precisely their light scattering properties. And maybe then we can say, well, this is a rod-shaped, or this is a round, or this is an oval microbe, and it's this big or this big. And I have a grant from the Department of Energy to build that equipment. But that's really now, I think, the next frontier. We know how to work with microbes that have pigment. Can we do something with microbes that do not have pigment, and can discriminate them between, say, little dust grains, because that's the other problem. If you have dirt, you have sand, and you have also, can I tell this is a clay particle, this is a piece of organic debris, and this really is a living thing. And we cannot do that right now. Very good point. Very good point.
A couple of years ago, there are some papers that talk about in solution fish.
In what?
In solution fish.
Oh yeah, in solution fish. Yeah, in suspension fish.
In,
Yeah.
in suspension.
Fish is fluorescence in situ hybridization.
Yeah, it's a technique that you can put a proof with a stain in the proof, and that proof goes to the microbes that you want, your target. And I read some papers that you can do that, and then they try to quantify that that cells with the proof using flow cytometry.
Yeah.
You know if somebody is improving that, but seems to be that because I read some papers and never read any other paper.
Yeah, that is very typical for flow cytometry. There's a lot of people that just take hematology instruments and they use it for a year and they get lots of data and then they just dump them in the literature and then they do something else.
Yeah.
And that is my problem with, so, you know, you can produce a lot of results. Yeah, I had a broke, I hybridized, this is my picture, and I'm going to do something. And maybe you do a postdoc, let's say, postdoc does it, postdoc goes away, project is
I think that because if you do that technique, I think that you can do a lot of things and different questions for several different
technology development and assay development is very time consuming.
Yeah.
And my problem with modern science is that people don't do it anymore.
Yeah.
They say, we have biotech companies, they will do it for us.
Yeah.
Well, maybe they will do it for cancer diagnosis, but they will not do it for oceanography. So, to do this right, you really need to spend the time, and you need to spend a couple of years just trying to figure out how to improve hybridization. There is one guy in Switzerland, Jakob Fernthaler, who I can get you the paper, who worked on in situ hybridization of flow. This is now 10 years old or so, and the Americans, Americans, the North Americans. Right. I know that Chilean fans get very upset when I say American. It's us. No, I'm Dutch. But they have a very short attention span. You know, you get a grant, you have 3 years, you got to finish it after 3 years. So you do not do technology development. You want results. And I don't know what it's like in Chile. Probably the same, yeah. And in Europe, it used to be that there was a fixed budget, so there was no time limit. But that has changed too. You know, as governments try to streamline stuff, you get money for a project, and you get more if you're successful. So, and I think that's quite tragic because technology takes time. Again, it's not commercially viable. If there's a commercial aspect, then you can develop technology and sell it, but who's going to buy it?
Yeah.
So realize that maybe you know you should have some consistency in your research. You're going to be most successful in science if there's some technology or some technique that you understand better than anybody else. And that takes time and it takes effort. So even if you do short-term projects, try to have a logical sequence of projects so that by the end of 10 projects, you know at least 10 times more about some technology. And no, I think the situ hybridization of cells and suspension is extremely important. I think because you could do RNA expression. You could not only ask what is your genome, but you could say what protein are you making now. Yeah. And maybe you don't have to do that in suspension.
Maybe you say after.
Yeah. So I would like to talk about that. I would like to talk about it, and so maybe you can remind me. This is not the right moment, but I would like to. And that goes for all of you. If there's something that I talk about, you think I really would like to learn more about it, then I'm going to immediately switch off my computer, and we're going to talk about something else and improvise. But this is a good point. Yeah, something like that.
Thanks.
All right. Any other questions? A question?
Quedaron todos claro cómo funciona el equipo, ¿no? ¿Entendieron bien cómo?
Es que
sí,
¿Hay un curso entonces?
No, después viene que ir con la presentación del input, con los láser y todo.
Ah, perfecto, ya.
So now it's time for
Let's do a break.
coffee and galetas.
Por favor, para romper el hielo.
Aquí ya una vez. Ya comieron todo, agua.
Es posible con una técnica normal que se ocupa para las lecturas oceanográficas de citometría, si era posible distinguir si había células vivas o células muertas y cómo era posible distinguir la materia orgánica fluorescente de las células.
Yeah, so, and those tests have been developed within biomedical research, and maybe some of those tests can be translated to oceanography and environmental microbiology. If you have a live cell, it will have a nucleus, a mammalian cell. Bacteria, of course, have DNA, but it's not in the nucleus. And the live cell is intact. It's nice and round, and the refractive index inside will be different from the refractive index outside, because you have different salinities and stuff. So, first of all, light will scatter from the outside. Whenever you have a change in refractive index, light beams will be deflected. So, live cells scatter. So that could be the first criterion. And I expect that the same would happen for, say, bacteria. That if you have a bacterium that is leaky, or the content come out and the outside world can come in, the scatter probably goes down. It's definitely the case for mammalian cells that scatter. Let me spell it, scatter. It's very dependent on whether the cell is intact or if it has holes in it. There's an exchange on the scatter. So that's the first thing that you could try. And we always measure scatter. Scatter is a free parameter. You don't have to stain, you don't have to have filters. So you should always measure scatter, and sometimes that gives you a clue if your cell is live or dead. The other property, of course, is that you could test for holes in the membrane. If I bring a big molecule inside, a molecule, and that goes through the membrane, and the molecule is inside, it will leak out in a cell that has holes in the membrane, but it will stay inside. So we can do two things. We can go put in molecules that bind to DNA, or we can use other molecules that are in the cytoplasm. And one of such molecules is fluorescein diacetate, which is a fluorescent molecule with two acetate groups. Does not fluoresce. It goes inside the cell. It will become fluorescent and become fluorescent. If there's holes in the membrane, it will go out, but if there are no holes, it stays in. So fluorescein diacetate can be used to detect living cells. The cells become very green, and green is a good color because it's not a very, it's not one of the natural chromophores that you find in algae. So green fluorescence is a good one. So it's possible that for oceanography you could use fluorescein diacetate to look for dead cells. The other one is to use DNA dyes. So some DNA dyes go through living membranes, some don't. So you could use a DNA dye that goes through a living membrane and accumulates in the cell. Some DNA dyes do not go in, DNA dye. And you can, if you see them accumulate in the nucleus, you know that the cell is alive, because, actually, no, the cell is dead, because those DNA dyes go to the pores. So there's several options. I personally do not know about studies that have done this for microbes, but I'm sure that you could develop an assay, or that there must be stuff in the literature. Oh, by the way, one of the books to consult whenever you are looking for something is Shapiro. Practical Flow Cytometry. I think it's available free on the web. Howard Shapiro reads everything, he remembers everything, and he writes everything down. So if you want to know something about the topic, you go to Howard Shapiro, and you probably will find the answers. His literature list in the back of the book is absolutely fantastic. So Howard Shapiro, Practical Flow Cytometry. So those in short are my questions. I don't think you need to read any of the other books about the introduction of flow cytometry. You know, there's lots of books, Introduction to Flow Cytometry. The only book you need to read, or need to have, because you can't read it, it's too much in it, is Howard Shapiro's book. So it doesn't clear very well. All right. Principles of flow cytometry. So I think what's going to happen, and correct me if I'm wrong, but we're going to do lectures in the morning tomorrow again, and then stop around noon.
Yes.
And then in the afternoon we go to the machine.
Yes.
And work with the machine. It's in a van, it's in a container. Can we get this many people in a container?
3 inside, the rest outside.
Maybe two.
You need oxygen, you need oxygen.
We can take a look.
Yeah, I think we probably should do it
Split into
in groups. So maybe you can divide into, we have 8 people, 10 people. 5 people is a lot. And are you going to run a machine and demonstrate how it works? Me?
Oye, ¿todos van a estar a la tarde para la... Toto, Víctor, también tú, vale, todo?
5 y 5, 5 and 5.
5 and 5, okay. But I think you or
Yes, we will.
Christian should do the machine, so
Yes.
that I can just say, you do it all wrong. And so be flexible, you know. Half of you get your phones out and your web browsers and play a game or something while the others are in the. So today I'm going to continue with the principles of flow sorting. Tomorrow we are going to talk about photon chemistry and how light interacts with dyes, and we're going to look at oceanography and other practical applications.
Sería bueno que mañana ustedes pudieran traer al menos una diapositiva de qué es lo que han hecho con citometría. They can bring one slide each one.
Good, good. And you give and if you have That's great. That's great. Maybe we should start with that tomorrow.
Yeah, we start with that, and then we continue, and I will give a lecture about the uses that we are applying here.
So I don't have to do anything tomorrow.
Yeah, of course. It's a long morning.
Perfecto. Okay, so here we are. Principles of flow cytometry, cell sorting. So we can measure physical, optical properties of single cells very accurately and fast. I forgot to say that we can do easily 1,000 cells per second. Actually, we can do 100,000 cells per second. It seems like a lot. How many seconds are there in an hour?
3,600.
3,600 seconds, so we can do, if we do 10 to the 5th, we can do 10 to the 8th cells. A billion, million in Spanish, I think.
A billion.
A billion?
No, sí, de billion.
Yeah, a billion cells, a billion cells.
1,000 millones.
1,000 millones.
Million, okay, million. Yeah, a million,
Mil millones.
Mil millones cells in an hour. In an hour.
1,000 millions.
Yeah, so that is a lot. There are how many inhabitants in the world? 8 million? 8 billion?
Bacteria total?
No, people.
Ah, I don't know. Bacteria.
Five.
But I think we can sort a cell for everybody in 8 hours. That should be fast enough. And it is not. It's not. If you want to do a bone marrow transplantation, you need 10 to the 10 cells. And then you have to, so that doesn't work for bone marrow transplantation, for instance. If you want a microgram of DNA, then you need to sort for 3 months. Just to give you an idea how hard it is. It's fast, but it's never fast enough. Well, it's like everything. You have an internet, but it's never fast enough. So, and then we can sort into fractions also at about, oh, this must be a mistake. See, I have the same number here, but this is more like 10 to the 5th per second. You can analyze, you can sort it about 1,000 per second. So we've seen that, we already talked about it. The difference here is that we have, it's fast, so the electronics needs to be okay, needs to be able to do that. We have to make the decisions very fast. We make 100,000 times a second, we have to say, I want that one, I do not want that one, so the electronics, the computers have to be fast. And we also have to have very good optics, because if we have a cell, it's very small, it's so small you cannot see it. If you have a laser and the laser illuminates a big area, then that light is not getting on the cells, so you're missing information, but it's falling on other things, so you get a lot of background noise. So you want the laser to be about the size of the cells, and that's not that easy. It's not that easy to make a light spot that is only 4 microns or 5 microns. And this is how it works. This is a nozzle piece. A conical shape, hole at the bottom, with pressure, push liquid through it. There's water coming out of the little hole, like a little squirt gun. You have those in Chile?
Yeah.
So we go. We make a little jet, and then and the diameter here is about 100 microns, so 1/10 of a millimeter. So this would be a millimeter, so it's all very small. And then we inject the sample at the core, and the fluid is going. It's not going very fast here, it's moving fastest here. So if you inject your sample, it will accelerate, because the cone narrows down, the fluid goes faster and faster, and then these cells can be held nicely at the center, and they come exactly at the center of the hole, one by one, come out as a laser beam, so the laser beam sees every cell. Very briefly, for about microseconds. So we talked about how many seconds are in an hour, right? How many microseconds are in a second?
3.6, but
No.
10 to the 7.
Microseconds. Oh, in an hour, yeah. Microseconds in a.
In a second?
In seconds, yeah.
1,000 seconds.
10 to the 6th, right?
10 to the 6th.
Yeah. So there are as many microseconds in a second as there are seconds in a month. Right? It's only 3,000 seconds in an hour, so there's 1,000,000 seconds takes a whole month. So if I do the cells at 100,000 per second, the machine most of the time is doing nothing. It's just sitting there. Give me a cell, give me a cell. And then it happens, and then everything has to just work right, and then it goes into the next mode again. The jet moves at about 10 meters a second, 100 kilometers an hour. So this is the speed here is that of a speeding car on the highway. So these cells come by and you say, oh, that's an erythrocyte, that's the prochlorococcus. It's not that easy actually. But it's a very tiny stream, so you can put your hand there and you don't feel like a car that is going 100 kilometers an hour hitting your hand. It's just like, anything else I need to say? This is fluidics. The people that make the machines have taken care of that. But you need to have fluidics when things just don't start, what do you call it? you don't have turbulence, so that and sometimes you do actually. Sometimes turbulence happens when you're cleaning and starting up the machine, and days later you still find your cells coming out because they were stuck to the side here and then they come out. So cleaning your instrument is important.
I have a question. You need to prepare the sample, or for
No.
example.
No, the notion sample, you just put it in.
In your case,
No,
you need
so,
to.
yeah, it could be, but in the water and the sea, you have other particles like.
Yeah, you don't care,
Okay.
because they all come by one.
Oh.
You say, oh, that's a particle I'm not interested in. Oh, yeah, that looks good.
But always you have to pre-filter samples if your sample line is
Well, you do here, probably, yeah. In Hawaii you
Because
don't,
of
because there's nothing in the ocean.
nothing in the ocean, but
Yeah.
it's present in pixels.
So, but if this is 100 microns, if the particle is, that's Shapiro's first law.
Okay.
It says a particle of 101 microns will clog a hole of 100 microns. So if you have a particle that's too big, that's the end of the experiment. So if your particles that you want are, say, 20 microns, the hole is 100 microns, you could use a filter of 80 microns, so all your particles come through, and you don't clog the hole. And yeah, that happens a lot in the beginning, that if you work with cells, or especially if you try to prepare them, you have a beautiful suspension, it goes great, and then you put an antibody in and things start clogging up, then especially if that happens inside the machine, you have filtered it, but now they start aggregating, then that's the end, that's the end. Suddenly you go from 100,000 cells a second to 0 cells an hour. Not good, not good. And in fact, and I think that you will say that too, you spend most of the time getting your liquid clean, cleaning your instrument. It's so important. If you let these instruments go, bacteria grow, you get biofilms, everything is bad then. So, now, and we have a clean sheet fluid, because, so I forgot to indicate that here. We have a big core of clean fluid, and we inject just a little bit, so that the fluid is going, we just inject a little bit so that the core, the sample is only at the core. So we, at this point, we have a flow of cells and there's clean fluid all around it. So now we can make a very tight light spot there, and these cells go through that tight light spot. And then we make a focus laser beam, focus it right at that point, and then we stop it, right? So it's like, yeah, it's like this. We stop the light so that if there is a cell, that's probably on the next slide, yeah. So when there's a cell and that cell is emitting light, scatter, and fluorescence and everything, we can look here and we do not see the laser, but we only see the scatter light. So the first possibility is to shield the laser light and look at the light that comes in the other directions. Spatial filtering. Second possibility is to use a filter, a bandpass filter. So if we want to look at green light, we can put a piece of glass in that blocks the purple light, but it transmits the green light. That's chromatic filtering. So we have different ways of seeing what we want to see. We could look for polarized light. Then we put a polarization filter in. And we can put detectors all around here, so we can look at multiple things, and we can have multiple lasers, so we can really do a lot of measurements here. This sort of summarizes it. Optics is basically a microscope. We have a cell here, a few microns. We have a microscope objective. The microscope makes an image of that spot. We have a screen with a pinhole. That's a spatial filtering. Only the light from this point goes on. If there's light coming from here, the lens will project it on the screen. It will not get through the little hole. This is our first way of removing all the light we're not interested in. If you,
There's also light here, there's laser beams, there's lights reflecting, there's fluorescent lights in the room, there's lots of lights, but we throw it all away, just like in a confocal microscope, and we only look via this hole to that spatial element. So the spatial filtering is very, very important, and you will see this afternoon how that is done. It's the most important thing, that you line up the pinhole that you sample very, very accurately. Then we have a collimating lens. Do people know how lenses work? Probably not. A collimating lens takes a beam that is not divergent, and turns it into a parallel light beam. Why is that? Well, we want to do chromatic filtering, we want to look at different colors, and these filters only work well if you put in parallel light. So in order to do the chromatic filtering, we need to make a collimating beam, and then we can put filters in and photodetectors and look at the light. So those are the two optical filtering techniques that we have. We have spatial filtering and chromatic filtering. We can also filter electronically, because if we have a lot of detectors here, we know that the signals must all happen at the same time. Right? If the cell is here, then all the detectors must say there's something going on. So I may use a scatter detector, because scatter is easy to measure. Fluorescence may not be easy to measure because it's very, very dim. And you could not look at the detector and say, now there's a cell, there's not a cell. But if you use the scatter detector to say there's a cell there, then I can tell the fluorescence detector, please tell me how much fluorescence you see. And that could be zero. So in that way I can measure a cell with zero fluorescence if I trigger with another. And that's called temporal. With a complicated word, electronic timing is temporal filtering. So it's by using a combination of spatial, chromatic, and temporal filtering, I can really remove a lot of irrelevant information out of the environment and say, this is the property of a cell. Here you see it. Here we have 3 pinholes. This is the jet coming out of the squirt gun. You see the cells go to the center of the stream. So this stream is maybe 60 microns, 60 micrometers. The cells only are in an area of about 5 to 10 micrometers. So barely, the cell just barely fits into that little channel. These are calibration beads. That's why you see such a nice fluorescent image. A video camera. How fast does a video camera work? What do you think? Movies. How many images per second do you get? Gadiel?
30 frames per second?
Yeah, 25. You know, a very fast video is 50 frames a second. How many cells do we have? 200,000 or 100,000 a second, right? So if you have a video image like we have here, then every image has 100,000 divided by 50. Let's say 50,000 by 50. That's easier. This is about 1,000. Every video frame will show you 1,000 cells. That's why you see this as a blur. But it really was a single particle coming by. But in a video image, you see 1,000. The integrated signal of 1,000 images.
Estas cosas las vamos a ver en el citómetro en vivo, o sea, tenemos una cámara y se ve eso, entonces si no lo entienden lo podemos revisar cuando bajemos el citómetro.
Yeah. So, so now we take this image. This is an image from the camera, and then only the light that is in front of that pinhole will go through and will be seen by the detector. So the detector doesn't see that, the detector only looks at that point. So you need to align that very carefully.
Why you record that in the video camera? Or it's just for...
Well, if I didn't have that, how would you know the machine is focused right?
Oh.
You wouldn't. So this is a way to focus it, right?
Ah.
I can move the lenses, I can move the pinholes. Maybe when I started out, the jet was here and the cells were there.
Oh.
And then I said, okay, I'll move the jet here, and I move the cells, the laser down, and now I know. It's like you are looking through, the detector is like looking through the keyhole of a door, right?
Yeah.
So you don't see anything in the room. So you have to be on the other side of the door to take whatever it is to bring it to the pinhole, and now suddenly, hey, I see something. So that's why we have a camera. We see 1,000 cells, but we don't care because this is the alignment camera. And then behind, is that here? No. Behind, so we were looking from this way, and we saw that everything was properly aligned, and then the photo detector sees, we're looking through the pinhole, and the cells coming by bleep, 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 at for 2 microseconds you see a bleep come by. And this is what it looks like in the real world. This is our nozzle piece. This is the transducer that makes the drops. And then, because we need to control that drop formation, I'll talk about it later, here comes the jet. You already see that there is some structure in it. The laser beam comes from there. The light scatters all around. This white is the scatter light. And then here we have an objective. This is the bar, see the scatter bar. And then the light goes into this lens, and then there's a pinhole back there that sees the light. And then we can have multiple lasers. This is a very old slide. We can get any laser you want now. And you see all these different lasers, they all come in, and they're all being thrown to the central part, and that's where you do your measurement. Chromatic filtering can be very complicated. So here we have a laser beam of 488 nanometers. That's the standard laser beam. Everybody always starts with the 488 nanometer laser. That's because 30 years ago we only had gas lasers, and the only laser that really was easy to manage was a 488 nanometer laser. Then all the dyes were formulated around 488 nanometers. But in this day and age with LED lasers and semi-diode semiconductor lasers, you can get any color you want. So there's no reason to use 488, but still historically all flow cytometers work with 488, which is actually a very difficult wavelength to make with diode lasers. So if you would build a machine for oceanography, you might not want to use 488 nanometers because it's a difficult laser and it's not particularly informative. Although we still do. Then you put filters in there. You can reflect the light. You can reflect the light in a particular direction so that you favor one polarization state versus another. You then can put absorbing and transmission filters in. You can have filters that reflect the light. For instance, a 650 long pass would pass 650, but pass light longer than 650 nanometers, and it would reflect light of less than 650, and then you can have your bandpass filters that only pick out one frequency. So you could, if you do an experiment, you could design your own filter combination. All these filters can be ordered and can be made for you. And you could make your own layout. Nobody does that, as far as I know, but it's very possible. So this is one of the easy things.
They are a little bit expensive, each filter.
Well, yeah, but not on the, considering the price of the instrument.
Yeah,
A filter like that is maybe $200. For me.
Special price.
For you, my friend. No, but no, that was not appropriate.
but I know that you can pick ones for $200.